So, this is explains zebra life pattern in phase preference and alloys, and what we do now, we just like what we did in nucleation in Zeldovich, we write down a kind of a diffusion equation kind of scenario, and then we go into that, and I'll now this time I'll describe a little bit more of what you mean by diffusion equation and how these things develops little bit more detail. Okay. Now, let us consider diffusion equation. This you know from your undergraduate very well, and it is actually just a part of time dependent statistical mechanics, which we will do much more later, but we need a little bit of it here, and it is very easy. This gradient, this quantity gradient here is a 3-dimension. It is 3-dimensional vector, that means ddx, ddy, ddz, nothing to be a, and j is the current term. So, this is called conservation of mass, that I take the derivative of position dependent composition C, and composition C is xa minus xb. Then this is the just the statement of the we will call it continuity equation, is a statement of law of conservation. That means if I have a like that, then I take an area here, then the particle coming there, if and then I want to consider change what is happening here, then the change inside will be the amount coming in and the amount going out, and flux is the j. So, dj dx, if this is x, that will be dc dt, and there is a minus because with more going out it will be less, and if it is more than so this is nothing but the continuity equation, and this is the one that we just described. So, this is the continuity equation, just the conservation, but that means we essentially say particle cannot be created or particle cannot be destroyed. So, it is intimately connected with law of conservation, but continuity equation is a very simple thing, and you might have faced it in your undergraduate, in electrochemistry chapter and kinetic theory chapter. Now, we know one more thing, this equation by itself is not complete because there are two unknowns. Now, what is done is something is extremely nice, which is called Fick's law. Remember what is Fick's law? Fick's law is, now this is an exact, but Fick's law is not exact, but Fick's law is an assumption. Fick's law tells that the flux is derivative of chemical potential. So, if there is more chemical potential, then matter flows from large chemical potential to lower chemical potential. Here I use U as a chemical potential. So, Fick's law is what you call constitutive relation. It is an assumption, and this assumption, as one tells, is kind of within a linear regime, that means small fluctuation regime, it is valid. So, this you can read these things in Google, you can read these things little in Wikipedia, but these are very fundamental, very nice things. So, so this is my chemical potential. They are essentially saying matter flows from large chemical potential, low chemical potential, large free energy to low free energy. However, it flows with a rate, and that rate is the diffusion, d by kBt. Okay, and kBt is put in here. If you could have guessed it, it is because that kBt can as well go in the chemical potential. So, this is a dimension of energy, kBt is dimension of energy. So, U by kBt is dimensionless. This, as you can see here, is J comes because this is composition or concentration. So, 1 over L cube, and this is L cube by T. This flux is L square, remember, amount of matter per unit area per second, right. So, flux is L square by T. This is gradient. So, you get number per area per unit time per area. So, this 1 over L square T. So, gradient comes with 1 over L. So, this 1 over L cube T, this 1 over L cube T, dimensional analysis. So, now So this is 1 over L square T flux. Now this takes care of that, and this is energy taken care of, and this is 1 over L here, and D is L square by T, and so D is L square by T. So there is some interesting thing here. So D is diffusion L square by T. Bear with me for a minute, and 1 over L, and then it is M L square by T square, and that is then L goes, then L cube by T cube, but I have a KBT, so that again T square by ML square, so that goes out, and 1 over L square by T, L by T, L by T, L by T, okay. If this is composition, then it is L by T, okay. So C is used as a composition, difference in mole fraction. So C is used as a dimensionless quantity. So if C is dimensionless quantity, then flux is 1 over L, and flux is number of particles by 1 over L square T. Okay, so this is 1 over L square, 1 over L square is L square by T, and this is 1 over L. Okay, so I think there is something a bit screwy up here, but we have to continue, and I'll fix it up sometime later, that these things. Okay, so now we continue it. Now there is the issue, either I am doing something wrong here, likely most probably it is correct, but one of the notation used here probably is different from what I have in mind, but you can figure it out probably yourself. So okay, so now this is the, but the rest of the things is okay. This is continuity equation, this is continuity equation, and this is the flux. This definition is correct, and the chemical potential, remember chemical potential is Z is dA free energy by density, that is the chemical potential. So here the chemical potential is similar, exactly same thing. Here chemical potential is U, chemical potential is functional derivative of free energy with respect to composition or concentration, that because so this is an exactly same thing as that, but this is the functional, because C, this C is a which is C is a let me, so CR is XAR and minus XBR, and that's I think is my my confusion. So this is a mole fraction, and this is a mole fraction of A, this is mole fraction of B. So if I have the particle like that, then I divide into grid. I'm saying something very interesting, so please listen carefully. So then I choose one of them, and I say this is my location R, and in that location now I find out what in this location, which is R, I find out what is the number of A molecules and what is number of B molecules. So what is then, that will give me the mole fraction. So A molecules minus B molecules. So that is the composition C. So the way to consider the position dependent composition is to consider your system divided into grid, and then each grid you go, you can make the grid very small, but don't make it too small so that it doesn't contain, they let it contain about 8 to 10 molecules, then you can see. So when they are 50-50 equal number of A and B, then you will have composition 0, but it varies from position to position, and because of the inhomogeneity that is being created, and also because of fluctuations. Okay. So now, so this is the definition of composition. So when I take derivative of free energy with respect to composition, that gives me chemical potential, just like in thermodynamics. So Fick's law is driven, Fick's law is diffusion gradient of chemical potential. this cavity might be the problem of the dimensional thing, but we can. Now exactly what I said before, the free energy, I am going to create a inhomogeneity now. I am going to create the free energy, it is really a lot of fun now. I am going to create from here the homogeneous, where in every grid my C is 0. From there now I am going to place where C is 1 and here and minus 1 here. So I am going to create through this the heterogeneity, and I already told you the way to describe heterogeneity is Ginzburg-Landau. That I already told you that Ginzburg-Landau allows you to get this free energy. This is free energy as a Fc. So this Fc, this quantity is really a lot of fun. This quantity is this thing. So this is the thing Fc. Okay. Now, and this is the energy you have to pay in order to create a heterogeneity. So this is the surface tension term. So this is the Landau term, which is the bare free energy, and this is the surface tension term, because I have to create surface. To create surface, I have to pay energy, and so combination of the two is a. So now, if I want to see the WL, if I have to create the WL, and I know how to create the WL, and I know that is just Landau. Now the beauty of these things that I can create single well to double well by saying if A is greater than 0, then I have a single well, that is a high temperature, then I quench to low temperature. When I quench to low temperature, A becomes negative. If A becomes negative and this changing, then this single one like that becomes something like that. So that is a very clever way of doing. So I can now use Landau free energy into Ginzburg-Landau, and I can do something very, very clever. Okay. So I combine the diffusion equation, dc dt. I had two things, one flux term, another term, one flux term, remember, one dc dt equal to minus del dot j, and I have a j term that is in terms of d by kbt delta u, and then u is in terms of del f delta c. These three things are combined here. So there is one del here, another del here, that gives del square, d by kbt comes out, and the third part delta f del c, or the chemical potential system. So three ingredients. So I get the diffusion equation dc dt d by del square. Now I can consider this equation in terms of fluctuation, but that can wait. We don't need to do that. We can work with this equation, this beautiful equation. Now what we do is the following. We are almost done. That we consider just like we did in nucleation, exactly the Zeldovich and all these things that we consider in infinitesimal fluctuations of position dependent composition. So I said, okay, there is a fluctuation delta c. Then I go back, I said, okay, Fc plus delta c is Fc, and I write Fc plus as a result of that fluctuation. As a result of this fluctuation, my free energy has undergone at a position r some small change. How do I do that now? Okay, I go back my Ginzburg-Landau and put in place of C plus del c, and here C plus del c. Now this quantity I can do a Taylor expansion, Fc plus del c, Fc plus df del c. This is just a first order Taylor expansion. Now, and this quantity del c plus del c square. So I now going to do that, grad c plus delta c square. So now I multiply. That means this, since this is a vector, this is a delta dot delta c, grad dot delta c. When I do that, I get delta c dot delta grad c square, and then grad delta c square. So grad delta c square is a small term, so that is neglected because it is a nonlinear or a quadratic in fluctuation. Then two terms remain, 2 delta c delta c. So I can now go back, I will be and put all these things together, and that is given here. You know, you put this term there, then you realize that this term and this term, these two can be combined to get Fr, this quantity, and I am left with this. I am left with okay, this combined. I am left with this term and this term which I collect here, and then I integrate these by parts, delta C, and I can get this term I integrate by parts, I will get delta square C delta. I brought the linear thing out, and then I do that, I am going little, I get the following equation. Delta Fr is this quantity. This is the one now I am going to use to find out my chemical potential, and when I do that, put it together, this is the equation one gets, the Smolkowski equation. Now the important thing is that with these equations are given there, you can, this is not difficult at all, it is just simple linear algebra, same thing you did in calculus. But the important thing is now I have an equation for small fluctuation, and that is of the following form. There is a diffusion, second order term, and the term dfdc. So in the next stage, one go and say, okay, I go back to original thing, that this equation is a very powerful equation, and lot of things can be done with the equation, but we are not going to do that now. We are doing something very simple. We are going to do just here. So my CR, my fluctuation I consider just around C0, little fluctuation here, this little fluctuation. Then I say, okay, my dfdc term there I can write like that, dfdc 0, and then second derivative. And this of course we know is dfdc here maximum is 0, so that goes to 0, I am left with this term. If I do that, then I go back and put it back here, dc here, du c is u plus c0 plus u, so it becomes du dt. So then I get du dt d del square minus k square df. So this is the final equation, what you call linearized equation. And then something very nice to it. So with this equation now, one very simple thing one can do is that we can say, okay, if I have the small fluctuations, what happens to that fluctuations? So this is my small fluctuation. Now, is this fluctuation going to grow or the fluctuation going to decay? If fluctuation going to decay, I am not going to get the phase separation or spinodal decomposition. But if the fluctuation grows, then there is an instability, and that indeed happens. One introduce a Fourier analysis and does a Fourier space analysis here, and one can show that if that, because this equation is fully linear equation, I can do a Fourier transform, these become dk square, these become k small k square, this k square, and so k square plus k4, and then you get this equation k square and k square k4, I take k square out and I just take the surface tension term out. So in the spinodal decomposition, then we are talking of a small fluctuation in this initial, let's say we call it linearized regime because u is very small, and the way, one of the way to study this kind of small fluctuations through a linearized equation like that is to go to Fourier space. We call this a stability analysis. So this stability analysis that we are doing here is a wonderful thing for stability of fluctuation. Even it's the same thing as the stability of that we do in the free energy with that means whenever you do a fluctuation, if the energy increases as a result of fluctuation, then the system is stable. Like if I here for example I give a small fluctuation, if it stays then it's stable, but if it is in a region like that, marginal stability, if it falls like that, then that's the free energy decreases. Here in this case gravitational energy, if by influence on fluctuation free energy decreases, then the system is unstable. So this is the way we talk even in thermodynamics, the stability and instability, just because we look into the first derivative and second derivative. The same thing we are doing here. We already have a beautiful equation for the evolution of the small fluctuation here, and the small fluctuation, and I want to know what happens to the small fluctuation, and this equation here is going to tell me what will happen to the small fluctuation. That equation already has a great character. It has a surface tension term which resists building of heterogeneity, and a free energy term which helps in the phase separation. Okay, because it is this term is coming from this term, that helps, but surface tension term, as I said, by diffusion, they do not like it, okay. They don't like creation of surface tension, that is why it comes with the negative term, and these two are opposite in sign, they fight against each other, and in that fight who wins? That is called stability analysis, and the way to go to stability analysis is just introduce the Fourier. Why we do Fourier? It is simply because this equation is linear equation, it poised beautifully. So, if I do Fourier transform, in k square will term, another k square will term, so k4 term. So, these k's go with this and k4 go with that, and that is exactly what happens, this k square and k square k4 term, and this is the k square term. So, now if I say okay, this quantity, my fluctuation grows, it grows or decays with this omega k. So, now I solve that, I said okay, if ukt is equal to e to the power minus wkt. So, this is my equation. From this equation, I did nothing. I said okay, I have introduced this definition, then I go back and do the Fourier transform. I find duk dt becomes omega k uk, and then that omega k is given by this term, and this equation means I have this solution. Now, if on a fluctuation, the fluctuation has to grow, then omega k has to be negative. If the fluctuation decays, then omega k will be positive. It is a very simple stability analysis that you probably have done in the stability analysis of your differential equations in your undergraduate. Those who have little mathematics course, they will have the stability analysis of the diffusion of a differential equation is a very important thing for a differential equation, whether it has a stable solution or not. Many solutions are neglected because they are not stable solutions. Okay, the same thing here we are doing, nothing really very fancy. So, now at the end of the day I get this solution, and omega k now is given by this thing. So, this is the constant term, not important. So, it is k square. So, important thing is that k square plus 1 by k dou, that is all. Now, this quantity, remember, is negative because this is falling down, this quantity is positive at function of k. Now, there will be a k when, so small k, this is positive, but when, so this quantity that is coming from here falling down, so maximum second derivative is negative. So, sorry, this is negative, but this is positive, okay. So, this is negative and this is positive. So, very small k, this quantity is negative, but large k, these become positive. So, when I go to large k, remember I have a negative sign in front of it. So, when a large k, it becomes positive, that means the fluctuations decay, but at a very small k, this quantity wins, and then omega k becomes negative. If omega k becomes negative, I have a negative sign, then these quantity become positive. That means once infinitesimal fluctuations grow, and there is a crossover, this is the crossover. So, below that wave number, fluctuations, this is really interesting, as I said here, that below that wave number fluctuations grow, but then large wave number fluctuations stable, and this is exactly like our nucleation kind of thing. There is a surface term, is a diffusion term, and there is a free energy term, and so below that Kc, system is unstable, but above that it is stable because this quantity is negative. So, this is the stability analysis, and that explains the Spinodal decomposition, that why infinitesimal fluctuations can give rise to growth of patterns, and the pattern that grows with the wave number Kc, because this is the where first time, because you are not going to go very large scale fluctuations, you are doing local small scale fluctuations, and you are trying to do local small fluctuations, and you find your fluctuations just decay. However, suddenly you can have a fluctuation, your particles A and B particles are brought together such that there is a fluctuation, a certain size of A, certain size of B are there, very much like nucleation. So these A and B are now can be stable now. So that particular is the Kc, that magical wave number is the Kc, and in Kc that pattern now suddenly stabilizes, and then we know that is the pattern that can evolve. How do you know that all these things we are telling is right or wrong? Well, people go and can calculate this fluctuation correlation function by X-ray scattering. This is called structure factor. Just like we did wave number Fourier transform, this is the static structure factor that one gets by X-ray scattering or neutron scattering. So the maximum scattering occurs towards lower, then what happens that one, when do you get scattering? You do not get scattering from a homogeneous system, you get scattering when there is an inhomogeneity, and because in order to scatter you have to have different regions of different density, okay, just like in light scattering you need to have different refractive index, and that exactly one sees that in X-ray scattering, that this peak, and as the phase separation progresses, the peak is the manifestation of there is these regions, and these regions move to a lower and lower k value. This is k with time lower value, that this is the longest time T3. So, and that means what means my patterns becoming thicker and thicker, and phase separation is going on more and more. So, the scattering shifts towards lower values. This is known as coarsening, very important thing in the phase transition language, coarsening, coarse graining. So, system is coarse graining itself, evolves toward a phase separated state. So, I think this is the end of the spinodal decomposition. To summarize that, it's a wonderful subject to end the phase transition for the time being. We'll back with the critical phenomena later, and this is the kind of situation we are describing, and this is the kind of coarsening behavior. So this is very different from nucleation, but at the same time exceedingly common and popular, and is not really taught in statistical mechanics courses, but as soon as you go into the realm of research, this is one of the first things that you face, just like nucleation. And I think students should be prepared for these kind of things, rather than knowing a lot of equations and lot of partition functions. They are fine and they get us started, but they do not really lead you to a very interesting and important areas of research, and don't allow you, for example, to read research papers on nanomaterials and other things, where people you will see they are always talking of nucleation, they thermodynamic control or kinetic control, they are talking of Becker-Dorin-Zeldovich, they are talking of spinodal decomposition. But this is it, because I think students should read at the level of BSc or MSc these kind of things. So this is where we stop now, and we'll return soon with another dose of phase transition, and then we'll go over to more mundane and but more detailed things of liquid state theory and more interacting systemizing models and phase transition, and many other things are there, like how to do binary mixtures, how to talk of surface tension, many other things. Okay.